everyone, this is Ashley with Aria Entertainment, and today I'm going to be covering What is Sound Part 3. So last time I said that I would teach you how to read a Fletcher-Munson curve, also called the Robinson-Dadson curve. The first thing you have to do is pick a Fawn curve to read. Now the Fawn curves are labeled from 0 to 120 by tens. So these red lines that you see are Fawn curves. Now, a Fawn is a unit of measurement that is related to how the ear interprets the loudness of a sound. Okay? So, after we pick a Fawn curve, I'm going to pick 40. After we pick a Fawn curve, we pick a frequency in hertz and follow it up to the Fawn curve you picked. So, I'm going to choose 100 hertz, and we're going to follow it up to the 40. It is right here. After that, when the frequency and the Fawn curve you picked meet, follow that point across to the y-axis to determine the sound pressure level. So let's follow this to the y-axis and we reach 60. So at 40 Fawns, 100 hertz sounds like 60 dBSBL, which is a regular conversation. Now let's talk about masking. Masking is hiding some frequencies with other different frequencies. Loud sounds mask soft ones, and low-pitched sounds mask high-pitched ones. So for example, if you have a 200 Hz tone and a 2000 Hz tone, the 2000 Hz tone will sound louder. But raising the amplitude of the 200 Hz tone while keeping the amplitude of the 2000 Hz tone the same will make the 200 Hz tone sound louder than the 2000 Hz tone. Now let's talk about velocity. Velocity is the speed of a sound wave, how fast a sound wave travels. While velocity doesn't affect pitch or loudness, it is used to calculate the length of one cycle. The length of a cycle is determined by dividing velocity by the wave's frequency. So wavelength, the symbol right here, is equal to velocity divided by frequency. And the wavelength is the distance a sound wave travels to complete one cycle. Remember that I said one cycle is when a wave completes one full motion of compression and rarefaction. Finally, we can talk about phase. Phase is the relationship between two or more sound waves at a point within their cycles, which is measured in degrees. So here we have a sound wave, one cycle of a sound wave. The sound wave starts at 0 degrees, then raises to 45 degrees, then peaks at 90 degrees. This is compression. Then goes back down to 135 degrees, and then goes back down to 180 degrees. Then from there, it starts going even further down to 225 degrees, then goes to 270 degrees, this is rarefaction, then reaches 315 degrees, and then ends at 360 degrees. This is the point where the vibration either stops completely or gets hit with another sound wave. When two or more waves begin at the same time, their degree intervals are identical, meaning they are in phase with each other. In this example, we have two waves, and they both start at 0 degrees. Because their degree intervals start at 0 degrees, they both start at the same time, they will increase in amplitude when put together. However, this specific example, when they both start at 0 degrees, their amplitude is the same, and their frequency is the same. The amplitude will double. Now the opposite also happens. if two or more waves begin at different times, they are out of phase. So for this example, we have one that begins at 0 degrees, and the other wave shifts to a 90-degree start. This means they are out of phase and will decrease in amplitude when put together. This example is a little more special, like the first one, because if the first wave begins at 0 degrees, and then the second wave begins at a shift of 180 degrees, they will actually cancel each other out. If the sound waves begin at partially different intervals, there will be constructive interference or destructive interference. Constructive interference is an increase in amplitude due to the compression and rarefaction happening at the same time. So with this example, we have a wave that starts at 0 degrees, and then another wave that starts at a shift of 45 degrees. But their amplitude is going to increase because the compression right here and rarefaction right here are happening at the same time. Now for this example of destructive interference, which is a decrease in amplitude due to compression and rarefaction happening at different times, this wave starts at 0 degrees, and then this wave starts at 270 degrees. So they will have destructive interference or a decrease in amplitude because the compression and rarefaction are happening at different times. So let's stop here. This is a very good place to stop. And next time, I will be covering timbre, sound envelopes, and analog and digital sound. Thank you.